Welcome to lecture 20. So, this is the last lecture of week 4. In this week, we have talked about basic concepts of optimization part 2, and specifically we have talked about optimality conditions for constraint optimization problems. So, we have talked about Lagrange multiplier techniques for equality constant optimization problems as well as inequality constant optimization problem. Then we have talked about Karush-Kuhn-Tucker conditions, KKT conditions. So, in today's lecture, we will take some examples and discuss them. So, we will talk about few examples in today's class. So, we are expressing a general problem with both equality and inequality constants as shown. We are minimizing the objective function and our inequality constants are less or equal to type. So, let us quickly review the KKT conditions. You first define the Lagrangian, then you write down the gradient conditions, which basically is del L del xi equal to 0. Then feasibility check, which basically says all inequality and equality constants must be satisfied. Then switching conditions, which says the Lagrange multiplier associated with inequality constant multiplied by the inequality constant will be equal to 0. Non-negativity of the Lagrange multipliers for inequality constants uj star greater or equal to 0, and regularity check, the stationary point must be a regularity point. The gradients of active constants must be linearly independent at the stationary point. KKT conditions are applicable only for regular points. So, first let us take an example with one inequality constant. So, the objective function is x 1 minus 1.5 whole square plus x 2 minus 1.5 whole square, and the equality constant is x 1 plus x 2 minus 2 less or equal to 0. We have talked about a problem with the same objective function and the constant was x 1 plus x 2 minus 2 equal to 0, not less or equal to 0, when we talked about equality constant optimization problem. So, we will define the Lagrangian. So, we are converting here the inequality constant to equality constant by defining a non-negative slack variable. So, you can write the Lagrange multiplier as this. You have this objective function and then the Lagrange multiplier multiplied by this constant converted to equality constant. So, Lagrangian is defined. So, the now necessary conditions are del L del x 1 equal to 0, which gives this, del L del x 2 equal to 0, which gives 2 into x 2 minus 1.5 plus lambda equal to 0. You also have to take del lambda equal to 0, which gives this, consider this, and also you have to take del L del sigma equal to 0, which gives 2 lambda sigma equal to 0. This is the switching condition. And then the non-negativity restrictions on the Lagrange multiplier and the slack variable. So, stationary point must satisfy these necessary conditions. You have 4 equations coming from del L del x 1 equal to 0, del L del x 2 equal to 0, del L del lambda equal to 0 and del L del sigma equal to 0. And you have 4 unknowns x 1, x 2, lambda and sigma. But note that these equations are nonlinear, so multiple solutions may exist. So, let us look at how you solve this set of equations. Look at the switching condition 2 lambda into sigma equal to 0. So, either lambda equal to 0 or sigma equal to 0. So, let us take first case A where you set sigma equal to 0. So, sigma equal to 0 means you do not need any slack variables. What it means that G is satisfied as equal to 0. So, G is active. Now, if you take sigma equal to 0, you will be able to solve this set of equations and you will get the solution as x 1 equal to 1, x 2 equal to 1, lambda equal to 1 and we have taken sigma equal to 0. Now, x 1 equal to 1, x 2 equal to 1, lambda equal to 1 is acceptable because lambda is positive. Sigma equal to 0, it is also non-negative. So, this is a stationary point of the Lagrangian function L or of the given problem. So, it is a candidate for minimum point. So, now let us consider case B where we will take not sigma equal to 0, but we will take lambda equal to 0. So, if you take lambda equal to 0 and solve this set of equations, you will get x 1 equal to 1.5, x 2 equal to 1.5, lambda equal to 0 you have taken and sigma square equal to minus 1, but this cannot be true. Sigma square or sigma is a non-negative slack variable. So, this is not a valid solution as it violates the inequality constant at point x because G plus sigma square will be equal to or G equal to minus sigma square will be equal to 1 which is greater than 0. So, sigma square is greater than 0, has to be greater or equal to 0. So, sigma square we are getting as minus 1, it means that the constant is being violated. So, x 1 equal to 1.5, x 2 equal to 1.5, lambda equal to 0, sigma square equal to minus 1 is not a valid solution. So, the valid solution is x 1 equal to 1, x 2 equal to 1, lambda equal to 1, sigma equal to 0. So, now you remember this figure we talked about when we talked the equality constant version of this problem. When it was equality constant problem, we had this as the feasible region, the line AB was the feasible region, but if I now say the inequality constant is x 1 plus x 2 minus 2 less or equal to 0, the feasible region becomes expanded. The feasible region becomes the line AB and the region below it. Note that we got the solution as x 1 equal to 1, x 2 equal to 1, the solution remains unchanged at point C. So, the optimal point remains same at point C. Also, the gradient of the objective function, if you evaluate, it becomes minus 1 minus 1, x 1 equal to, put x 1 equal to 1, x 2 equal to 1, and you get the gradient of the objective function as minus 1 minus 1. You can also evaluate the gradient of the constant will be 1 1. So, note that the gradient vector of the objective function and the gradient vector of the constant function, they are in the same line. So, they are lined up, but they are pointing in opposite directions. So, now let us take another example. This time the objective function is x 1 square plus 2 x 2 square plus 3 x 3 square, and we have two inequality constant as x 1 minus x 2 minus 2 x 3 less or equal to 12, x 1 plus 2 x 2 minus 3 x 2 less or equal to 8. Again, so we will first write the problem in our familiar form, where we consider the inequality constant as less or equal to 0 type. So, this can be easily done. This becomes x 1 minus x 2 minus 2 x 3 minus 12 less or equal to 0, and this becomes x 1 plus 2 x 2 minus 3 x 3 minus 8 less or equal to 0. So, now we can define the Lagrange function. So, we can define the Lagrange function by taking the objective function and add the first inequality constant multiplied by its Lagrange multiplier, then add the product of second inequality constant and its associated Lagrange multiplier. So, the Lagrangian function is defined. So, now let us write down the KKT conditions and solve them to obtain the stationary points. So, first gradient condition, del L del x I equal to 0, f is L. So, del L del x I equal to 0. So, del L del x 1, del L del x 2, del L del x 3, all these derivatives will be equal to 0, and this will lead to these three equations. So, you take del L del x 1 equal to 0. So, del L del x 1 is del x 1 gives 2 x 1 plus u 1 plus u 2 equal to 0. Then del L del x 2, so it gives 4 x 2, then you get minus u 1, and then you get 2 u 2 equal to 0. Similarly, you get del L del x 3 equal to 0. So, you get three equations from the gradient conditions. Then the switching conditions, u 1 g 1 equal to 0, u 2 g 2 equal to 0. Then the feasibility condition, g less or equal to 0. So, g 1 less or equal to 0, g 2 less or equal to 0. Finally, we will have the non-negativity restrictions on the Lagrange multipliers associated with the inequality constants. So, u 1 greater or equal to 0, u 2 greater or equal to 0. Now, we have these 9 conditions we need to solve to find out x 1, x 2, x 3, which will be the stationary points, and of course, u 1, u 2 will satisfy the conditions u 1, u 2 will be greater or equal to 0, u 1 g 1 equal to 0, u 2 g 2 equal to 0. So, if we look at here equation number 4, u 1 g 1 equal to 0. So, either u 1 equal to 0 or g 1 equal to 0. So, let us first consider case A, u 1 equal to 0. So, from the first three conditions 1, 2 and 3, which basically you get from the gradient equal to 0, you can obtain x 1 equal to minus u 2 by 2, x 2 equal to minus u 2 by 2 and x 3 equal to u 2 by 2. Now, if you put this x 1, x 2 and x 3 value in equation 5, you will get an expression for u 2. So, you get u 2 square plus 80 u 2 equal to 0, which can be written as u 2 plus 8 equal to 0. So, either u 2 equal to 0 or u 2 plus 8 equal to 0, that means either u 2 equal to 0 or u 2 equal to minus 8. But both u 1 and u 2 has to be non-negative, they are greater or equal to 0, u j greater or equal to 0. So, we take u 2 equal to 0. So, now if u 2 equal to 0, you look at x 1 equal to x 2 equal to minus u 2 by 2 and x 3 equal to u 2 by 2. So, if u 2 equal to 0, x 1 equal to 0, x 2 equal to 0, x 3 equal to 0. We have already assumed u 1 equal to 0. So, this u 1 equal to 0, u 2 equal to 0, x 1 equal to 0, x 2 equal to 0, x 3 equal to 0 basically satisfies all these conditions. All these conditions are satisfied by x 1 equal to 0, x 2 equal to 0, x 3 equal to 0, u 1 equal to 0, u 2 equal to 0. So, now let us consider the other case g 1 equal to 0, which is x 1 minus x 2 minus 2 x 3 minus 12 equal to 0. Again, from here 1, 2 and 3, we can write this. How? From 1, 2 and 3, you can get an expression for x 1, x 2 and x 3 in terms of u 1 and u 2, like 2 x 1 equal to minus u 1 minus u 2. So, x 1 equal to minus u 1 minus u 2 by 2. Similarly, for x 2 and x 3. Then you can put those x 1, x 2 and x 3 which you have evaluated in terms of u 1 and u 2 and obtain this. So, this equation when simplified will give 17 u 1 plus 12 u 2 equal to minus 144. But since both u 1 and u 2 have to be greater or equal to 0, it is not possible that 17 u 1 plus 12 u 2 will be a negative quantity minus 144. So, this will not lead to a valid solution. So, hence the solution set for this optimization problem is what we obtained for case A, u 1 equal to 0, that is x 1 equal to 0, x 2 equal to 0 and x 3 equal to 0. So, that is the stationary point which satisfies all the Kronecker conditions. So, it is essentially a KKT point. Now, let us ask another question. You consider the problem shown. We are minimizing an objective function in two variables and we have three inequality constants. We say the point 7 6 x 1 equal to 7 and x 2 equal to 6. Does this point satisfy KKT condition? So, first let us check the feasibility. So, put x 1 equal to 7 and x 2 equal to 6 in each of these three inequality constants. So, we check that inequality constants are satisfied. Also note that first and third inequality constants, that means G 1 and G 3 are satisfied as equality constants. So, first and third constants are active, they are 0, whereas second constant G 2 is inactive. So, now let us compute the gradient of the objective function and the gradient of the constants at the given point x 1 equal to 7 and x 2 equal to 6. You can find out the gradient as shown. We have seen that the first and third constants, that is G 1 and G 3 are active and second constant G 2 is inactive. Now, for a point to be a regular point, the active constants gradients must be linearly independent. So, the gradient G 1 and the gradient G 3 must be linearly independent and they are linearly independent. So, the point is a regular point and the KKT condition will apply. Also note that the Lagrange multiplier for inactive constants should be 0. So, when G is satisfied as less than 0, its associated Lagrange multiplier is equal to 0. When G is satisfied at G equal to 0, that means active constant, the associated Lagrange multiplier will be non-negative, greater or equal to 0. So, now let us check the gradient condition. So, we can write del f del x I plus u 1 del g del x I plus u 2 del g 2 del x I plus u 3 del g 3 del x I equal to 0, I equal to 1 to t. So, if you do these calculations, you will get this. We have already evaluated these gradients. So, you just put it here. Now, this system is satisfied by u 1 equal to 2, u 2 equal to 0 and u 3 equal to 4. So, note that all our conditions are getting satisfied. The Lagrange multiplier for inactive constant should be 0. The inactive constant was G 2 and the associated Lagrange multiplier is 0. The active constants G 1 and G 3, the Lagrange multiplier are 2 and 4. So, non-negative. So, all these conditions are satisfied. So, we have checked the feasibility conditions, the gradient conditions, the non-negativity restrictions on the Lagrange multipliers. So, since all the conditions are satisfied, the point 76 is a stationary point and a candidate for an optimal solution for the problem. The point x 1 equal to 7 and x 2 equal to 6 is a KKT point. Now, let us consider a problem where you have an objective function in two variables as f equal to 2y minus x square. Your inequality constant x square plus y square is less or equal to 1, and then two constants on x and y, x is greater or equal to 0, y greater or equal to 0. So, how do I formulate the Lagrange function here? So, the Lagrange function can be formulated usual just following the same technique. So, consider x equal to 0, y equal to 0 as independent constants. So, you formulate the Lagrangian function as the objective function 2i minus x square plus the inequality constant x square plus y square minus 1 multiplied by its Lagrange multiplier. Then I write x greater or equal to 0 as minus x less or equal to 0, then multiply by its associated Lagrange multiplier. Similarly, I write y equal to 0 as minus y less or equal to 0 and multiply by the associated Lagrange multiplier. So, you have the Lagrange function. Now, you can apply the KKT conditions. So, you will be writing del L del x I equal to 0, the gradient conditions. Second, you will check the feasibility. The feasibility will be x square plus y square minus 1 less or equal to 0, minus x less or equal to 0, minus y less or equal to 0. Third, you will check the switching condition, which says u j g j equal to 0 and j equal to 1, 2, 3. And finally, you will have u j non-negative. So, this will give you the equations which when satisfied, which when you solve, you will be able to find out the stationary point that satisfies the KT conditions and you can obtain the KKT point. With this, we will stop lecture 20 here.